So hello students, a warm welcome to MRS Math class. Hope you are fine. So today I am going to discuss about a new chapter, that is linear equations with constant coefficients. Okay. Already I have taken so many classes related to this topic. First I discussed about the basic concept of differential equation. Next I discussed about the first order and first degree differential equation. Then I discussed about first order but of higher degree differential equations. If you have not seen the videos, you can click on the I tag and get all the videos related to this. Okay students, so let us start the topic, that is linear equations. That means the linear equations involving derivatives. That is linear equations, that means linear differential equations with constant coefficients. So if we will see the general form of linear equations with constant coefficients, then we can write that is dn of y by dxn plus a1 into dn minus 1 y by dx n minus 1, okay, and so on up to our a n minus 1 dy over dx plus a n into y equal to some constant function x. Okay, so here this capital X is a function of x alone, okay, and this a1 a2 up to an are arbitrary constants. Okay, so this equation 1 we can write symbolically like dn, okay, plus a1 into dn minus 1, okay, plus a n minus 1 into d plus an into y equal to x. Okay, so here this d represents derivative, that is dy dx. Okay, again in shortcut we can write f d of y equal to x. Okay, so this one we can take as equation number 3. Okay, where this f d is equal to this one dn plus a1 dn minus 1 up to an minus 1 d plus an. Okay, so now we'll prove two important properties. Okay, and using these two properties we'll prove two important theorems, which is easy but carefully we have to see. Okay, so let us say this is property 1, okay, that is f d of cy, okay, equal to c into f dy. Okay, so if we prove this, then by taking LHS to this side, that is f d cy, okay, we can write f d as this one, right, dn plus a1 dn minus 1 an minus 1 d plus an, right, into cy, correct. So this c if we will take to first, then c into this is dn plus a1 dn minus 1 up to an minus 1 d plus an into y. Okay, so this one is what c into f d of y, right, which is equal to RHS. Okay, it is very important and easy one. Okay, so now we'll see property number 2. Okay, here we'll write property number 2. It is this property 2, that is f d of y1 plus y2, okay, is equal to y1 into f dy fd plus y2 into fd. Okay, so let us prove this. Okay. Take this one as LHS. Okay, that is fd of y1 plus y2, that is this one dn plus a1 dn minus 1 up to an minus 1 d plus an into y1 plus y2, right? So this one equal to, we can write y1 into this one dn plus a1 dn minus 1 plus an minus 1 d plus an, right, plus y2 of dn plus a1 d n minus 1, right? So 1 an minus 1 d plus an, right, which is equal to y1 into fd plus y2 into fd, right, which is our right hand side. Okay, so these two important properties we will use to prove the important theorems. Okay, so let us see what are the theorems. Okay. Now we will see what is homogeneous linear equation with constant coefficients. Okay, that is, if the right hand side, this x, which is a function of x, okay, we will do as 0, we will take as 0, then this equation will convert to, let us say this is as fd, okay, and this is y, okay, is equal to 0. Okay, so this is homogeneous linear equation. Okay, now we will discuss about the solution of this homogeneous linear equation. Okay, so first of all, the theorem is, okay, let us say theorem 1. What is the theorem? The theorem tells that if y1 is a solution of equation, let us say 2, then Cy1, okay, Cy1, okay, where this C is any constant, okay, Cy1 is also a solution of equation 2. Okay, if y1 is a solution of this equation, then Cy1, okay, is also a solution of this equation. Okay, so using the property 1 we will solve. So proof is, since y1 is a solution of equation 2, we can write fd of y1 equal to 0, right? Let us say this is as equation star. Okay, now we have to prove that, fd of Cy1, right, is equal to 0. Now fd of Cy1, okay, this one we can write as c into fd of y1, yes or no, by using the property 1. So which is equal to c into fd of y1 is 0, which is equal to 0, right? So you got this one, fd cy1 is 0, 0. That means cy1 is a solution of the differential equation 2. Okay, so we proved the theorem 1 by the help of property 1. Okay, now we will go to the theorem number 2 and we will prove this by using these two properties. Okay, so the theorem 2 says that if y1, y2 to yn are n linearly independent solutions of equation 2, okay, then the linear combination c1y1 plus c2y2 up to cn yn is also a solution of equation 2. Okay, so before going to the proof of the theorem, let me discuss about what is linearly independent and what is linearly dependent. Okay, so write down first linearly dependent. Okay, linearly dependent. So what is linearly dependent, or LD, sometimes you can write LD. Okay, so what is this linearly dependent? So the functions y1 of x, y2 of x, okay, up to yn of x, okay, are said to be linearly dependent, okay, LD, in some interval, okay, in some interval, then there exists some constants, okay, let us say alpha 1, alpha 2 up to alpha n, okay, in bracket, which is most important, that is not all 0, okay, alpha 1, alpha 2 up to alpha n, not all 0, okay, this term is very important, not all 0, such that alpha 1 y1 plus alpha 2 y2 plus alpha n yn equal to 0, okay, then y1, y2 up to yn are said to be linearly dependent. Okay, so if the functions y1, y2 up to yn are said to be linearly dependent, okay, in some interval, such that there exists some constant alpha 1, alpha 2 up to alpha n, not all 0, okay, then it will satisfy this equation, okay, then only we will say that they are linearly dependent. Okay, now we will see what is linearly independent, okay, that is Li. Okay, so write down the functions y1, y2 up to yn are said to be linearly independent in some interval, okay, if there exist constants alpha 1 equal to alpha 2 equal to alpha 3 to alpha n equal to 0, such that in that interval alpha 1 y1 plus alpha 2 y2 plus up to alpha n y1 equal to 0. Okay, then we will say that the functions are linearly independent. Okay, there in linear dependent condition, so not all 0, but in linear independent case all the constants are 0 and it satisfies this equation, then we will say that these solutions are linearly independent. Okay, now we will prove the theorem. Okay, so we understood what is linearly independent and what is linearly dependent. If we understood, then we will go to the proof of the theorem. The proof of the theorem. Okay, what it tells: if y1, y2 up to yn are n linearly independent solution of equation 2, that means y1 is a solution of equation 2, right? So we can write f d y1 equal to 0, right? Similarly, y2 is also a solution of this equation 2. We can write f d of y2 equal to f d of y3 equal to f d of y4, right, up to f d of yn equal to 0. We can write from here, from this statement, right? Now from here again we can write f d of cy1, okay, or c1 y1 equal to f d of c2 y2 equal to f d of c3 y3, okay, up to f d of cn yn equal to 0 we can write. Okay, where this c1 c2 c3 are some arbitrary constants. Okay, here I suppose to write that c1 c2 to cn are constants. Okay, so this one we can write by the help of theorem 1. Okay, which we proved by using property 1, right? Now from here we can write c1 f d of y1, right, equal to c2 f d of y2, right, equal to cn f d of yn equal to 0 we can write. Okay, again this one we can write as say everything is equal to 0, right? So if you take the linear combination, that is c1 f d of y1 plus c2 f d of y2, right, plus c3 f d of y3 up to cn f d of yn is equal to 0 we can write. Okay, yes or no? If each term is 0, then the linear combination is also 0, right? From here we can say that c1 y1 c2 y2 cn yn is also a solution of equation 2, right? Because this one is satisfying to equation 2, right? So we proved these two theorems, right? Now we'll discuss about the general solution of this type of differential equation. Okay, general solution. Okay, so if we are considering a nth order differential equation, then we are getting n arbitrary, n linearly independent solutions, right? So that c1 y1 plus c2 y2 plus c3 y3 up to cn yn, let us say this is u, okay, is also a solution of the differential equation, right? So that we can write fd of u equal to 0. Okay, similarly if we consider another solution, particular solution v, okay, then we can write fd of v equal to some function x, right? Now if we'll take the linear summation, that is fd of u plus fd of v, okay, then we will get fd of u as 0 plus fd of v is x, then we will get x. Okay. So this proves that this is a general solution of the differential equation, right? So from here we can conclude that the general solution is equal to complementary function plus this particular integral. Okay, so this complementary function we are getting from here, in particular integral we are getting from here. Okay, so in the next class we will discuss about the general solution of this type of differential equations, how we can get the complementary function of the equation, okay, with more and more examples. Okay students, I hope up to this the basic things I discussed is clear to you. Okay, so next class we will see. Okay, thank you.